take a webinar on that. Now, the good thing about recording, about this recording, is that you can just sit back and listen. If you miss anything, or if you have a question that comes up later in your mind, you can always reference this. We get it up on the YouTube site usually about 2 weeks later. But if you do have questions while we're going through the slides, feel free to stop us to either use your question panel, and I'll explain in a moment how to use that, or go ahead and just wait till later. Send us an email if you like, or just ask questions as they come up in the question panel. So a little bit about myself. I'm Jay West. I am an educational consultant. I work for Retrotec, and that's my real email address, jwest@retrotec.com. Again, I'm joined by Ken Levenson. He's an AIA, a CPHD, and a CFO. And he's down. And Ken, I'm told you're down with OPP. Is that true? So yeah. So, and also, Ken, I just want to say that if you want to say, just kind of introduce yourself, say hello. But I want to let you know before you get started that I did not add your email address, and just in case, you got emails from people, out there, like, that are like your ex-wives or something like that. I didn't know if you had any out there, so.
Yeah, Ken at 475.com, and I think it comes up at the end of the presentation as well.
Okay, cool. Well, glad to have you, Ken, and a fun guy. Yep. He says he's got a bit of a cold. He's going to be joining us. So are you in New York right now?
Yes.
Okay, great. So he's going to be joining us from New York. And he is on the recording as well. He will be available for questions, and we have John Drillinger and Joe Medosch in the background. They'll also be supporting us with some questions if you have any technical stuff that you want to ask about. And again, this little slide here is just to remind you that this will be on our YouTube site. We have tons of information on our YouTube site. Ken, do you guys have a YouTube site, or you have social media, right?
We do have a YouTube channel.
And what's the name of that?
What?
It's a
if you go to 475.com on our video, we have a video page that links you to it.
Awesome. So yeah, so this one will be this webinar will be available. The recording of it will be available then in about 2 weeks. But you also can find plenty of videos, plenty of education, building science stuff, and discussion on 475 on their website or on our site, retrotec.com. Right now, I just want to check to see if everybody can hear us. So to let you know, the control panel that's popped up there on your screen should have popped up on your screen. That's the way to sort of control everything and how to interact with us. If you don't feel like interacting, if you just want to sit back and relax, that's also really great. You can just use that little red button to minimize that control panel. Thank you, Mr. Wintley. If you do want to interact, and I strongly recommend you do, because really the power of a webinar is the fact that you can interact, you can ask questions, you can add your comments. There's going to be several points where I'd like to ask you questions and see what you think. You really want to get the most out of this, because your time is money, your time is important, and time is very important to us, and it's a great honor to have your time. So I want to make sure that I give you and Ken wants to make sure that we really give you everything you need, and that we customize it to your needs. So please use that question panel, not just for questions, but to make notes, to provide us with feedback, or even make comments. And thanks, Dave. Ken is a little bit muffled. Ken is coming in on a phone receiver. That's the most comfortable and best way for us to figure it out. And like I said, Ken's got a bit of the flu, so he's just muffled in general, right, Ken?
Yes.
So thanks, but that doesn't mean you can hear us. So if you can't hear us, this is always my favorite part. I do this every week. I talk about what to do if you can't hear us. I explain to you verbally what to do if you can't hear me verbally. So hopefully this screen will help a little bit. But go to this guy right here, push settings. That'll open up this window right here, and that's how you can quickly and easily control your sound. So we have a few session objectives, and I always mention this every week. Of course, they're not learning objectives because a learning objective would be something that's demonstrable. So at the end, there would be some kind of assessment of what you've learned. We won't be doing that. But we do have sort of points or things that we think are important that we want to touch on. One is that we want to make sure that you just kind of understand what the passive house standard for air tightness is. Ken's going to be explaining that a little bit here in the beginning about what the standards are, how do you test for it, and what they mean. We want to make sure that you understand what some of the best ways to test passive house buildings are. I'm going to try and go through that a little bit, talk about some best practices. So not just how to, just follow, verbatim the standards or the protocols, but actually how to some best practices and some things that we've learned from experience. We're going to look at what some of the obstacles to reaching that passive house air tightness are. And I think Ken's going to do a good job of talking about those obstacles and then basically solutions. What are some of the tricks and tools that help overcome those obstacles to reach the air tightness standard? I want to just acknowledge a hilarious comment here from Mr. Reed Rollins. That's the benefit of the webinar is that you can't catch the flu from the speakers. Good point. That is another benefit. I'm going to have to bring that up next time. But at this point, I want to ask, is there anything else? Did anybody sign on because they thought this was about, there was the topic was going to cover something else, or was there any specific things that they want to hear more about? So if that's true, just let us know through the question panel. In the meantime, I'm going to move on. A little FYI here, a little FYI about pH. Do you know, but in 1893, the first fully functional passive house was actually a Fram, a boat of Fridtjof Nansen. And I really, first of all, let me apologize for being brutally American to all of our European folks that are joining us. I am so sorry about destroying not only the English language, but any other languages. In fact, all other languages. So, but it turns out that that this Fram, this boat that belonged to Mr. Nansen, it was lined with tar felt. It had a cork padding underneath that. On top of it was a deal paneling. Does anybody know what deal is? On cue. There's a thick layer of felt and then a airtight linoleum on the inside of it. And then all that was held together with the air paneling. Now, mind you, these are the sides and bottom of a boat from 1893. The total thickness was about 15 inches. Sound familiar? The skylight was protected by 3 panes of glass, also sounds familiar, and he described his ventilation as excellent. So in a book that he wrote, he mentioned that the Fram here I'll try and do an accent. The Fram is a comfortable abode where the thermometer stands at 22 degrees above zero or 22 degrees above zero. We still have no fire in the stove. So that was my Irish accent because I couldn't figure out anything else. So that was pretty interesting. It's not a new idea, and it's been working for a long time. The idea of what we can do, or how we can design and build buildings that actually that perform better. So a little bit again, just a real quick overview. The basic criterion of the passive house: super insulation. It's got to be thermal bridge free. It's got to be ventilation with heat recovery. So that's not just, so we'll talk more about that, I think, next week in about 2 weeks, right, with Aubrey from Zender. But we'll also be talking about, today we won't be talking about heating and cooling demand, which is about 4,750 BTUs per square foot per year. And then air tightness being 0.6 ACH at 50 pascals. So those are all the criterion, but today we're really just going to focus on the air tightness part. So, so what is that air tightness standard? Well, the standards here I list, but I want to ask Ken, if you can, to talk a little bit about. And Ken, I'm going to try and hand over the keyboard to you, or the mouse to you now, and give you the baton so you can talk a little bit about.
Sure.
Stuff.
So, thank you. Good to be here. Thanks, Jay. And yeah, there's a few slides here, and we'll go back and forth. So just wanted to first touch on the whole idea of airtightness and what are we defining as airtightness, and it's changed pretty dramatically over the last couple of decades, and in the U.S. in particular over the last few years, where we're measuring airtightness and we use this ACH50, where we see 7 ACH50 on the left, and ACH50 is air changes per hour at 50 pascals pressure. 50 pascals pressure we're developing with a blower door, which Jay's going to be speaking about at length, pressurizing or depressurizing. The 50 pascals is about a 22 mile an hour wind equivalent that we're putting on the building. And so it's really an important measurement in terms of determining the energy efficiency, the energy losses through the leakage through the envelope of the building. So historically, as recently as 2009 in the energy code here in the U.S., 7 ACH50 may have been considered airtight. Now the code's coming on. We have new requirements for 3 ACH50, more than doubling of the airtightness. Up until recently, the U.S. building science community has really felt that 1.5 ACH50, another doubling of airtightness, was the limit of what we can reasonably expect in commercial construction in the U.S. But then along came Passive House and kind of changed the paradigm again and perhaps forever, demanding that the upper limit of what was required was 0.6 ACH50, more than cutting it in half again. And now we see regularly buildings coming in at 0.4, 0.3 ACH50. And the point here is that these buildings are getting dramatically tighter. Our understanding about airtightness has changed, and what was passable to get us the airtightness and the approaches to airtightness previously no longer hold true necessarily. One thing that we want to look at, can we flip the slide, Jay? It doesn't seem to be flipping for me. Thank you. So I just wanted to review here up front some of the different standards. So we just sort of went through a scale of the standards, but just in reference, on the left we have a column of airtightness standards that apply to volumetric measurements and relate directly to the energy use. So these are the measurements that are going into the energy model, into the PHPP for the Passive House calculation. The 3 ACH50, which we discussed before for the 2012 residential code, Energy Star for home at 3 ACH for zones 4 through 7, and Passive House at 0.6. And we also have a series of measurements that are surface area measurements that are more geared to the performance of the envelope on a leakage basis, per square foot leakage basis. And the GSA, the General Services Administration, has a standard, Energy Star High Rise, the Army Corps of Engineers. FIAS Plus has just adopted a new surface area standard of 0.05, and Passive House also has a surface area standard that's recommended for buildings above 140,000 cubic feet of 0.033 CFM 50 per square foot. So you have a sense of the different relationships there. Next, good. A few of the common standards in terms of testing, there are two main ones really, ASTM E779 in North America, and then if you skip down to the EM, European norm 13829 standard. And the Passive House is airtightness is based off of this 13829 standard method A. And what Passive House does in addition to that is do an average of the pressurization and depressurization. So if the numbers are different, your ultimate airtightness number is going to be the average of those two numbers. The important thing to realize, go to the next slide, please.
I think you've got control now. You want to try it again?
I do.
Okay, there you go.
Okay, great. Thank you. The one thing to just note regarding the ASTM standard and the EN standard is regarding the building volume, and that they are measuring slightly different things in terms of the volume, and they can be significant when you're comparing numbers. So it's not quite apples to apples, but the E779 is the overall outer boundary of the volume of the building that you're measuring against, and the 13829 is really the usable condition space from sheetrock to sheetrock is the way to think about it. The floor construction's gone, the wall constructions are gone. It's really the truly interior intentional space. So it is a significantly smaller volume than E779. To keep that into account. I'll be coming back in a few minutes after Jay and discussing some of the strategies involved.
Cool. So let's talk a little bit about that air tightness, that 0.6 ACH at 50. I wanted to kind of talk about some of the ways that we test for that. So first, let's talk a little bit about what you need to test. Let's talk about the fans, the gauges, and the frame and the panels. So here's a typical setup from Retrotec. And you'll notice that there is a difference here in if you look in the size of the blower. So this generally is, that's a duct tester. And that's a duct tester that comes with a frame, comes inside of a box. It comes with a DM32 manometer, an umbilical, which is our sort of our cords that are wrapped together, and then an array of different plugs, different range plugs that go into our orifice here. Point being that if you are testing a residential passive house, you don't necessarily need to have a large fan, a full-size fan. However, you can use a full-size fan, but normally this should suffice. So you add that fan to the DM32, and you end up with these guys kind of fitting into one of several types of panels and frames, but I think we're going to talk a little bit more kind of focus on this one, which is a window frame and panel, and I'll give you an idea of why I think that one's a better one to use. Not necessarily the only one to use, but a better one to use. So we're going to talk next about how you prepare to run the test, how you get everything set up. But before I do that, I want to ask, are there any questions so far? I know we're moving pretty fast. We're doing a pretty good job here. I think we're about 21 minutes in. Any questions? Feel free to type them in. All right. So we've got a question about ERVs, HRVs. So if anybody, if John or Joe want to respond to that. Yes, so that does. Yeah, Mr. Berry, the question is, can you use a regular Retrotec blower door setup? You absolutely, positively can. But I'm going to talk about a little bit about some of the new things that we have, the new products that we have out there that actually you can use as well. Good question. So let's talk first about the gauge setup. So if you want to run ACH with our gauge, with the Retrotec DM32, all you have to do is just press on the results, the area here, the channel B. Just actually physically touch this area, touch that part of the screen. It'll take you to all the results, and you can just choose ACH. So you don't have to run it at CFM50 and then take that out of the gauge and then calculate outside of the gauge. It's actually done. The calculation is done inside the gauge. Choosing your blower door fan. This one's a little bit more tricky. So you'll see here that what we've done is you touch this, you touch the fan that you have, same as the other one, you touch the screen, but it's going to take you to a list of blower door fans, and underneath the blower door fans it actually is listed not just the full-size fans but actually the duct testers. This is an important detail to note. because that same fan, that 300, if you're using it as a duct tester, will be listed separately and will actually have a separate icon if you're going to use it as a duct tester. The reason being that with the attachments and with the flex tube, the flex duct, that we're going to have a little bit different sort of flow curves. So it's real important when you're setting up your gauge and when you're using a duct tester to do the blower door test, that you make sure that you choose the 300, not the 340. Is that okay with everybody? All right. So now that you have that, now it's just all about putting the volume in. Again, very simple. You touch the settings button. It's going to take you to this screen. You touch volume, and then you just type in the volume of the house. And now it'll take you back, and you'll see right here, now you have actually a volume listed. Now I want to point out that right here, I've actually taken out the actual measurement. Over here we have cubic meters, but it could be cubic meters, it could be square feet, it could be, I'm sorry, cubic feet because it's a volumetric measurement, right? But the point being that this gauge does have built into all the gauges, you do have the option to use metric or imperial units for any of the testings or any of that stuff. So again, real smart gauge, it's got all that stuff's kind of built in. All right, I'm going to pause for a second before we go on to the next. Let me give you a second to ask any questions if you have any. I do see the question here about at what level of tightness do we expect to need an ERV. So I'm going to leave that until a little bit later once we get to that. Oh, it looks like John got in there. Thanks, John. All right. So a little bit about, somebody asked a moment ago, if we can actually run a full-size blower door, and yes, you absolutely can. To my mind, I mean, you basically have kind of a choice here. You can either use our full-size blower door, and this one's the 1000, and watch out because soon we have the 5000 coming out, which is got some range plugs of its own, a little bit different motor, a little bit different size. It's actually a really nice piece of equipment. But this is the 1000. Or you can use a full-size panel and frame with the 300 fan, or in this case, this is a 200 fan. Or you can actually use our window frame and panel, which I'm going to be talking a little bit about here in a moment, to test the house. So you have sort of your choice there of panels and frames and fans. Any questions about that? Awesome. A little bit more about that panel frame. So if you haven't seen the new frame, it has now the attachments to corners actually snap into place. You just sort of take the top piece, snap it into the side piece, and then together they hold pretty nicely, and when you're ready to take them apart, you just push the button and pull them out. Both full size and the smaller window frame are like that. However, you can see that the window frame, it can expands or contracts to fit most windows, and obviously it fits nicely and tightly in here. It's going to be lighter, easier to install. It comes with its own frame, and this frame has a hole, and right now the iteration we have has a drawstring, but we're looking at some improvements to make that even tighter. Question here from Mr. Sawkins: is there an upgrade for the older frames? Joe, can I ask you, can the new corner pieces, can they buy those new corner pieces, and can they just be easily screwed into the older frames?
It does not work that way. They're debating on seeing if we can come up with a solution to do that, but the old corner pieces are actually cut at 45s with a little insert with a little ball release on the back, and these are actually now cut square. So they don't actually swap one to the other. We are trying to evaluate if that's a way to actually convert one to the other. So at this point, there is no way to just upgrade your existing frame.
Thanks, Joe. It's good to have a posse. We've got quite a crew here today. Answer. I think this is a good day to answer. Good day to tune in, guys, and ask questions. Thank you so much for your question. So once you've got the fan in there, depending on how tight the house is, you can add plugs. Now, generally, our 300 fan comes with 3 plugs included. I'm not sure if this is the same The same plugs are included in the European version. I apologize for that, but generally you've got your 29, your 47, and your 74. So you can start with it open. You can add that's the 74, the wider one. You can add a 47 or 29, but basically the point is that these are tighter. We can test lower pressures. We can even go so far as to add even smaller plugs, all the way down to a 1, where we can literally test a pinhole. And in some of these passive houses, and I know some of you passive house builders, especially in Europe, might actually need to test a pinhole. So those are some of the things that you can actually do with this fan. And that's any questions about that? All right. Move on a little bit. So what are some of the best practices for testing? This is really actually a pretty quick and simple sort of section. Test at the window. So yes, you can absolutely test at the door, but let's be honest. We know it's a proven fact that we are going to get leakage around the frame, no matter around the panel and the frame. You can put it in as tightly as you like. You can really get it in there as tight as possible, but you are necessarily going to get some leakage around that frame. So obviously, if you have a smaller frame, and I don't know if it's obvious here, but this is actually a window. So if you have a smaller frame, you're going to have less linear leakage necessarily if it's installed apples to apples, as we say. So that's one of the reasons why you want to do that, why you want to test at a window. Another reason is that when you have a blower door fan in a door, you're not testing the leakage around that door. That door is going to be open. So you can see here, if this was a door, obviously we're not testing the window here because the window is open and we have a frame in here. So we're obviously not testing this one. So whether we're doing pressurization or depressurization test, it's a good idea to, I think, and better idea to try and test from the window rather than from the door. Also, you want to test at multiple locations. Now, of course, Ken pointed to the fact that you want to pressurize and depressurize, but I would say you want to try it in several different locations. So if you are testing at the door, try and test at multiple doors. If you are testing at the windows, test at multiple windows. And again, this is another sort of slight benefit of using the window frame, is the fact that it's very easy to move from window to window. It's not as cumbersome, not as difficult to set up, and you don't have so much stuff to drag around. So I want to pass it back over to Ken. Do we have any questions at this point? All right. Any questions? And Ken, I think you should still have, let me just check here. Yeah, you still have control of the keyboard or of the mouse if you want to forward through it. But yeah, any questions, let me know. I'll be in the background and try and help you out. Thank you.
Great. Thank you, Jay. And so what we want to do is go through a little bit of the basic building science and some of the design considerations and construction considerations in terms of achieving passive house level air tightness. So I'm not, let me see here. It's not moving for me, Jay. My computer. There we go. So first thing we always like to note, why the air tightness is so special in passive house, and it's special in building science in general, second only to keeping the rain out of the building. And after air control, we have vapor control and thermal control. So this is sort of the order of importance of our control layers. And why is it second only to water control? Next slide. Because it's disproportionately affecting such fundamental aspects of our building performance. Next. The indoor air quality. And basically the fundamental idea is that you can't control the quality of something unless you control it. The only way you're going to control air is within an airtight enclosure. Next.
Ken, give it a shot. I think I might have fixed it. Is it working?
I'm hitting my advance.
All right. Sorry about that.
Sorry. So just as a quick example here of uncontrolled air quality. We see here CO2 readings over 2 days where they're getting their fresh air from opening and closing windows. And you see each time they open the window, the CO2 level drops dramatically. You can have good air, but it's sort of all over the place. And by contrast, if we have an airtight environment, next slide, we have controlled air quality within an airtight environment with controlled ventilation. And we don't have a completely flat line, but the CO2 level is not only below the code requirements, in this case in Germany, but under the recommended levels. So basic health issues. Next slide. Comfort, drafty, uncomfortable houses, older houses, even newer houses. The drafts, next slide, need to be overcome by systems, mechanical systems at the perimeter, you know, it's never a good thing or an efficient thing. So we want to bring airtightness and bring comfort. Next. The wetting of the enclosure is something that not everyone thinks about, but airborne wetness of the enclosure is a major liability to the enclosure's longevity. Everyone thinks of diffusion. Here's a classic building science slide. On the left is water diffusing through a sheet of gypboard over one winter heating season, and on the right, same gypboard sheet with a small air leak. And we go from a third of a quart of water on the left to over 30 quarts of water on the right, exponentially different. So huge liability in terms of wetting of the enclosure. Next. Heat loss. We get to our basic efficiency and of the building, that air movement around through wind washing insulation can dramatically reduce its effectiveness. Next. I'll just answer the question, is that 30 quarts per year? That's over a heating season, over the winter, the course of the winter, given the conditions that Building Science Corporation set for that test. Not a year. That would be over the winter time is the time when interior humidity would be moving with the air pressure through the enclosure towards the outside. So back to this slide, the exponential energy savings as realized by airtightness, you might think of it a bit like having a sweater in a cold breeze without a windbreaker around it versus one having a windbreaker around it. It's been measured that, you know, similarly insulated enclosure, leaky versus airtight, to have a performance difference of almost 5 times, 4.8 times difference. So we're talking about fundamentally different performance driven by the airtightness. And we see this in the energy models. As we change the airtightness numbers, the energy demand, the heat demand, the cooling demand numbers going up. And having airtightness allows us to right-size the HVAC equipment as one of the key benefits in the economics of the upfront costs of building a passive house, is that you can dramatically reduce the mechanical systems, and having that airtightness gives predictability to the design, to the system. So in trying to reap these benefits, trying to hit these incredibly airtight numbers, when we look at designing airtightness, really the idea is that continuity is the thing we need to think about and drive towards continually. And on the left is the classic diagram with the red pen going around, where you never want to lift off the pen. You want to look at particularly at those intersections where the windows are penetrating, where the floors are penetrating the walls, where the wall meets the roof, that we have continuous airtightness. There's no break in it whatsoever. And in addition to that, you see that red line going around the house was on the inside of the insulation. And we definitely recommend that your primary air barrier be on the interior of the insulation layer. That what this does is it keeps the conditioned air within the conditioned space, and it really helps protect against condensation risk. Because if we don't do that, we have something like the diagram on the right where air can move into the insulation layer through the construction, meet cold surfaces, we have condensation and moisture damage. At the interior as well of the insulation, the air tightness layer can double as a vapor retarding layer. And so continuity, we talk about in contrast to discontinuity. And one example that we like to show in sort of a disconnected approach to air tightness is where you have something like spray foam applied between the stud bays, forming the airtight layer in this case. And you can achieve air tightness with this, but it is much less reliable and predictable, and is increasing the chances for issues, because here you have a joint, regularly. The air control layer is stopping and starting every few inches in each direction. So you're multiplying the points of potential problems. Again, the idea of connections, and in particular, the joints between the walls, the roof, the floor, the walls. It can't be overstated enough to look at those details and see that your control layers are being continuous through them. Penetrations are a huge liability in terms of air tightness, and we like to identify, and there are many different ways of approaching it, but the windows and doors, we have ducts and pipes, wires, beam penetrations, joist penetrations, all of these things we want to identify, address carefully so that we have continuity. Every penetration becomes part of the air control layer.
Hey, Ken, can I ask you a question?
Sure.
So, I apologize to everybody. I forgot to mention in the beginning that I'm a passive house, certified passive house tradesperson. Worked with these materials myself before, and I wanted to interject here when we talk about penetrations, because by far, from a tradesperson perspective, this is absolutely the most difficult to deal with, wouldn't you say?
Yeah, absolutely. I mean, and we try to reduce the number of penetrations, which I'll get to in a moment, and absolutely minimize the problems that way.
Right. And one of the things that I wanted to point out here is when we're talking about these penetrations are almost always going to be dissimilar types of material. Or pieces of material like this that are going to move, dissimilar pieces of material right here where we have this synthetic material that is running through a organic piece of material. We'll see plastics, fibers, all these different things that expand and contract at different levels or at different rates. And can you tell me again, back to these slides, how do I'm seeing tape here. I'm seeing
right.
How is that different from something else when we're talking about expansion, contraction, and movement?
So the idea is that these materials are allowing the different components to expand and contract and move. The building will move and maintain the continuity of the air tightness. So we see in particular around the wires at the bottom, the multiple wires, and the duct pipe at the top and the middle, the EPDM gaskets that stretch tightly around the wires and the ducts and allow the ducts to move. And those EPDM gaskets are connected to the membranes or wood sheathing with solid acrylic pressure-sensitive adhesives that set up and molecularly bond. So these tapes are also made to be able to move with the construction and maintain their adhesion and maintain the continuity of the air tightness. On the right, we see, or actually on the lower right, Yep, sorry. So you've got me going here. The joists have a felt tape going around them that will be plastered in to the brick wall. So any number of different ways and materials that we look at forming this continuity. Go to the next slide. So when we're going through looking at this continuity, looking at the details, the penetrations, the one thing we definitely push for to have a couple of clear drawings in the construction set that are outlining in section and plan, hopefully the airtight layer, the location of it, and that the details carefully locate the components of the airtight control layers and showing how they're moving through critical junctures. Very important to realizing and making it easier to hit. Next slide. One thing to quickly note is just the idea of the airtightness budget, as it were, with reference to materials, different materials that you're using. The materials that we're relying on for airtightness are actually airtight. We have the dotted line across the top representing the 0.6 ACH50 of the Task House standard, and this is a study of European OSB sheathing boards, so not directly applicable to here in the U.S., but very illustrative, where you see a wide range of airtightness from one group of sheathings to another. So on the far left, in the dark line, you have a sheathing that is almost as leaky as the Pass House standard itself. So it would require absolute perfect application to hit the standard, whereas the group of materials in B are very airtight, and you have a wide margin to hit the Pass House standard. So we want to use as tight materials as possible. OSB. Here we've seen issues in Europe, and we've actually just started to see some issues in the U.S. Excuse me. And we've seen a couple of examples, not widespread, but where they have had leaky OSB. So we want to be on the watch for that going forward, and all the materials carefully considered. Next slide. These control layers, we want to protect them. It's really important that once we've achieved these connections, we've got the right materials, the installation, that they're protected for the long haul, that they remain robust and durable. And great ways to do this is outboard of the building by back-vented rain screens, as well as back-vented roofs, and decoupling the weather, what's going to take the brunt of the weather, the sun, the atmosphere from the control layers. And on the inside, next slide, what we'd like to see is a service cavity. So here we have, you can see on the right, the inboard airtightness layer is the Intello membrane and smart vapor control. And so inboard of that, we have horizontal strapping of 2x3s laid flat. And within that zone, the electrical is placed. And by doing this, we're able to literally eliminate hundreds of penetrations through our control layer and really reduce the penetrations to just the windows and the doors and the basic services. And to the extent that we can eliminate these penetrations, we're going to increase our chances for success and long-term success. So a service cavity is something that we see becoming increasingly common going forward. And it may or may not be insulated depending on the energy model and the specifications of the project. Next slide. One thing to watch out for is you've got this built and all in place, and then our trades are coming along, the plumbers and electricians, God bless them, and they're cutting in new holes and cutting new holes for services through our control layers. So we need to keep a sharp eye out for these happenings and make sure that they're located and fixed. Next slide. Right. There we go. So one way we like to do this is a sign that we have. It's available for download from our website. Is signage to be put around the job site, much the way you would have no smoking signage, to have airtight building signage to remind the construction workers that they just cannot cut and drill any old which way, and that if they see holes through the control layers, that they need to report it. It needs to be part of the culture of the job site. And along these lines, oh yes, and then, you know, of course we want to inspect, verify, and repair. And one of the big things, this sort of an earlier vintage blower door from what Retrotec is showing you today, perhaps not quite as accurate then, but a start. And what we like to see is that you are testing. We like to say, especially in the early projects, testing early and often, and finding those holes, tracking them down, and making the buildings tighter and tighter. Next slide. So a final note on just the basic construction planning of it, and some basic things that we think are really important is to have a team meeting really upfront, identifying key personnel, and hopefully running a fan pretty early in the job site, even if you can't get an air tightness measurement, but people get a feeling of air leakage and can feel the leaks. It really can change the way the crews are working in the building, and they become, and all the tradespeople can become sort of watchmen for leaks and maintaining tightness. Training, we like to see more and more in the specifications by architects actually write in a requirement that a key person or somebody on the team has taken passive house tradesperson training, so that it is embedded in and can really be passed on directly. Regarding sequencing in general is so important, but really the big idea is to not enclose the air barrier until you've hit the number that you need. Because once you start enclosing it, there's no going back. You can't find it. If you're not sure where the leak is coming from, it's a real problem, and it can be either incredibly costly or you abandon the effort at some point. And then finally, that first blower door test, especially in the early projects, to do them as early in the process as possible. You know, when teams are very confident and they have experience, they'll do just one blower door at the very end of the project, like when the paint is dried, and they will be done. But short of that, we definitely recommend doing earlier blower doors. It's a really great learning tool for the whole team. And I think that is it. There's my email address and Twitter handle, and certainly happy to take any questions. Sorry if I sort of rushed through that a bit. I did want to make sure we had time for discussion at the end and cover the ground.
No, a great job. I mean, that's perfect timing. I did want to mention too about you had mentioned we talked a little bit there about running the fan and about training, and I talked about testing, and often the question comes up, who can actually test the building? So I know it doesn't at this point. I have not seen, unless there's been a change, and I'm not sure about the U.S. standards, but it doesn't really specifically say, right, who has to test or what certifications they need to have, because I noticed you mentioned the training part.
Right. No, really, the third party is the critical thing.
Mm-hmm. Right.
Of course, everyone is assuming that they're competent, but there's no verification per se about that.
Mm-hmm. So one of the things, and we talked a little bit about, one of our session objectives was looking at obstacles and how to overcome those obstacles. So when we're talking about the actual running the blower door and the obstacle of actually getting those tests, I want to point out two things. One, test early, test often. but it doesn't always have to be by a third party. That's standard, when you're actually looking for the certification test. Yes, call in a third party, but we're finding even in non-passive houses, even in large, we're talking about air barriers for large buildings or any number of buildings where people are doing duct sealing or have air tightness testing for ducts or for shells, that the actual builder is benefiting from actually running the tests themselves before they call in the third party. Reason being, you're paying someone, however, whatever, say X amount of dollars to do that test. Well, if you fail because you haven't run a blower door yet, and you're not sure if you're going to hit that target, you're going to have to pay that person to come out a second time.
Yep.
Yeah. So, and that's just So.
No, agreed. The one further thought I would say, the one thing we've seen is just not even putting in blower doors while they're constructing, but just put in a good construction fan in a window, and they're just letting it run while they're building. And so they're picking up a lot of things sort of on the fly as they're working.
Absolutely. The other thing to mention too is when we talk about the sort of the training that you need to actually accurately run that blower door, especially when we're talking to builders or contractors who are just sort of getting into the passive house field or building efficiency field, and they're kind of wondering how they can get trained. And something that we try and mention all the time is that we at Retrotec, we not only provide these training webinars, but we also have an online manufacturer certification. So if you buy any of our equipment, you're going to have access online to our certification to certify that you actually know how to use that piece of equipment. So if you're thinking about building a passive house and or you're building passive house but you're just starting to, if you want to stop paying other people to run the test, or if you want to just run the test for yourself, or you want your crew to know how to do that, we're going to make sure that you're certified to do that. Any questions about that, guys? All right, so I'm thinking verbally going to answer this one. Have a question here. Do the Retrotec larger blower doors perform to the same accuracy as the passive house model fan? And that's two things. So just want to make sure that you understand that that fan is actually a duct tester fan. It's just the 300 fan. And so it's not necessarily the frame and the panels are more intended for passive house, but actually can be used for several other iterations. But the answer to your question, is it as accurate? Absolutely. We're still using the exact same the same gauge. We're still using the DM32. That's going to really be the where the majority of the accuracy lives or is built in. The only difference between the larger fan and the smaller fan is that the actual volume of air that can be moved. And Joe, I think you wanted to add something.
Yeah, thanks. One of the challenges is that the cloth for a blower door is leakier when you're going to use the full-size blower door than you would for the larger duct tester, only because there's just inherent leakage in the system itself. So if you're trying to reduce the leakage that's inherent in your test, the best thing you could do is use a smaller cloth, smaller frame, smaller control over what you're testing, versus having the larger blower door, larger opening around the fan itself, larger frame. All that stuff adds up to the fractions that passive house people are always after. So if you are looking for the tightest possible test, again, you want to use that front door as an enclosure and actually test out of the window. So there's multiple reasons to really want to go smaller to get a better impact, if that helps.
Definitely. All right, so if we don't have any more questions, we're going to close her down for the day. I just want to say thank you so much to everybody who joined us, especially some of our friends from overseas. I know it's a little bit later there. Oh, when testing at such low ACH, what range of accuracy can you expect? Anyone want to answer? Anyone want to speak to that? What level of accuracy can we expect? I would say accurate.
Well, I can help you. All of the fans are calibrated to very low and very high numbers at 25, 50 pascals, 75 pascals. So, they go down to a very small range and a very high range based upon their calibration. So they're used to trying to test at those low numbers as it is included in their calibration.
Yeah, good point, Joe. I should mention that even though I don't have the exact number offhand, that's a really specific and really technical question. I can tell you that we do have a ISO certified test chamber that all of our equipment is tested in, is calibrated in. So that would be whether that be the fan or the gauge before it comes out of our factory, it's been tested to the absolute highest standard of accuracy. Okay. So thanks so much, guys. Really appreciate it. I see that we do have a request for more passive house webinars. We have one coming up about HRV and ERV, which is not specifically about passive house, but is definitely applicable to passive house. Joe, what do we have coming up next week?
Yeah, next Tuesday, same time as we are right now, I'll be doing duct leakage to outside and advanced duct leakage applications. So we'll do the basic challenges, but also what happens when you're trying to do leakage outside, but things are not always accessible. So it'll go through the basics to the more complicated testing protocols with duct testing.
All right. Well, thanks again. Your time is very, very important to us, and we really, really appreciate you joining us, being part of the family. Speaking of joining the family, thanks Ken and John for joining the family. It's good to have you guys. It was really fun sharing this time with you, and I learned a lot. Hopefully you guys appreciate it, and let's do it again.
Absolutely. Thank you. We're very happy to join. It's a good time.
Okay. Anything else you want to say about Ken that I forgot to mention?
No, just everybody should welcome to take a look at our website. We have lots of videos, an active blog, building science blog, and downloadable drawings. So we are all about sharing information, and so happy to do this webinar, and hope we have a chance to do another one.
Yeah, definitely. All right. Thanks everybody.
Terrific.
Auf Wiedersehen.
Bye-bye.